this lecture, we're going to go ahead and talk about polynomial functions. This will be sort of a rehashing of old concepts. A lot of students seem to be fairly confident with polynomials. But what we're going to do is actually approach this from a conceptual standpoint, specifically for the polynomial function part of it. In reality, what we're going to do really is just review some old definitions, specifically for functions and stuff like that, and for polynomials. And then we'll talk about the domain and range of a polynomial function. As far as prerequisites, you'll have to know quite a bit about functions, how to evaluate them, all the little bits and pieces of what a function is, the idea of domain and range, and we'll have to also know quite a bit about polynomials. All the little definitions involved with polynomials. If you're lacking any of these skills, please go back to my prerequisite lectures, which would be really, I have a whole bunch of lectures on functions. I have some lectures on domain and range, and I also have a ton of lectures on polynomials. So if you're lacking in any of these skills, or if you find that as you go through this video there's something that's absolutely confusing to you, please go back and review those concepts. Now, the official definition of a polynomial function is a function that has the following form. P of x is equal to a sub n x to the n plus a sub n minus 1 x raised to the power of n minus 1 plus a sub n minus 2 x raised to the power of n minus 2, and so on and so forth. In other words, each of these powers here are just losing 1 as time rolls on. So if n were 3, let's just say, then you'd have x to the third there, and you'd have x to the second, and then x to the first, and so on and so forth. And as you can see, the only restriction that we have is that these n's all have to be natural numbers. Well, the original n has to be a natural number, but if the original n is a natural number, like 1, 2, 3, 4, 5, or 6, or so on and so forth, not 0 though, if the original number is a natural number, then all of the other powers also are natural numbers, right? So if n were 7, then we'd have a 6th power and a 5th power all the way down to the first power, which would be the exponent on that term right there. Now, it does not need to have all the powers in between. So, for an example, the following could be a polynomial function. F of x is equal to, I don't know, let's do like 17x to the 4th minus x plus 1. That's a polynomial function, even though we're missing some of the powers in between x to the 4th and x to the 1st here. We still have a polynomial function. It doesn't have to include all the powers in between. So really what makes a polynomial function is just that you have some expression or some function here where the powers on your variables are just counting numbers. Okay? Also note that it is traditional to note a polynomial function with a p of x, although it's not required. I used an f of x down in this example, but a p of x is generally commonly used for the introduction of a polynomial function like we did here. Now let's talk about the domain of a polynomial function, and I had mentioned right at the beginning of this very short lecture that we're going to talk about the domain and the range of polynomial functions, but it turns out range of polynomial functions is very difficult to tack down at this point. Very, very difficult. In fact, if you go back and watch the lecture on polynomials, or I'm sorry, on domain and range, I had mentioned that domain is generally okay to find. We can find the domain of a function pretty quickly, but the range often requires us to graph the function. And so that's what we're really working for here. We want to be able to eventually graph a polynomial function so we can determine its range. But for right now, let's go ahead and talk about the domain of a polynomial function. And one thing to note about polynomial functions is that their domain is all real numbers. And note my notation here. I use the R with the double vertical bar on it. That means the set of all real numbers. So the domain of any polynomial function really can include any number I can imagine. And you kind of see that with just a simple example. If you had a polynomial function like g of x is equal to 3.18 x to the 15th power minus x squared plus 1.2 or something like that. Domain is set up or found by asking yourself, what can I plug in for x? I mean, what's valid? And recall that when I talked about functions or domains of functions in the past, I've said there really is only two, possibly three things that restrict the domain of a function. So let's recall that conversation. In general, the three things that will restrict the domain of a function are division by zero, having negatives underneath radicals, even radicals, and then finally negatives or zeros as the inputs of logarithms. A simple example of each of these, something like if you had a function defined by 1 over x minus 4. Well, the domain here would be everything except that x cannot equal a positive 4, because if it did, you'd be dividing by 0. The second example, you could have some type of q of x is equal to, oh, I don't know, let's say the fourth root of, we're just going to make these easy, x plus 2. Well, I know that the domain, in other words, the set of x values I can plug in, has to follow this rule. X plus 2 has to be positive or 0. In other words, that x must be greater than or equal to a negative 2. So this would define my domain. My domain is all x values that are greater than or equal to negative 2. Just like in the first example here, the domain would be all x values that are not equal to 4. In other words, everything going from negative infinity all the way up to 4, but not including it, and then union that set with everything starting at 4 and moving on to infinity. And in interval notation, the second interval would be everything starting at negative 2. And in fact, if you see how I wrote that, there is a mistake there because, because that should include negative 2. So let me go ahead and do that. Everything including negative 2 and climbing all the way up to infinity. So those are our domains for the first two functions. And then finally, the very last function here, I can't have negatives as the input of a logarithm, nor can I have 0 as the input of a logarithm. So if I said that, let's say, L of x is equal to the log base 5 of, well, let's do like x squared plus, not plus, let's do x squared minus 4. Well, in that case, I know that x squared minus 4 would have to be strictly greater than 0, because I cannot have whatever x squared minus 4 is, it cannot be negative, nor can it be 0. So that would imply that x squared minus 4 would have to be greater than 0. We've actually done these in the past. You can factor this, and you get that x minus 2 times x plus 2 would have to be greater than 0. Okay, and then you would draw a number line here, and you would test values. So let me just draw a number line, and what I'll do is I'll insert what will turn x into 0 first of all. So I know that means that x equals 2 and x equals negative 2 are what we call our critical values. So I'm going to put negative 2 on here and a positive 2 on there. I know one thing about this. If x is positive 2, then this first factor right here is going to turn into 0 if x were a positive 2, which means that this whole entire left side would turn into 0. 0 is definitely not greater than 0, so that would be an issue. So I already know immediately that x cannot possibly equal 2. So we'll go ahead and put an open hole there. And same thing can be said about negative 2. X can't be 2, nor can it be a negative 2. And then if I want to find out when x is positive, I'm sorry, not when x is positive, but when x squared minus 4 is positive, I'm just going to plug in test values. So let's say we try a negative 3. Let's see what happens when we plug in a negative 3. You can either test it with this x minus 2 times x plus 2, or you can plug it into the original inequality, x squared minus 4. I'm just going to plug it into the original inequality because it seems a little bit faster. So if I plug negative 3 in there, I'll get 9 minus 4, which is 5, which is definitely greater than 0. So I happen to know that in this region, which is less than negative 2, I know that our function will have a positive input. X squared minus 4 is going to be positive. In this middle region between negative 2 and positive 2, I'm just going to select the most obvious value, which is 0, to test. If you plug that into x for x squared minus 4 here, you'll get that 0 squared minus 4 is negative 4. And negative 4 definitely is not greater than 0. It's actually less than 0, so it's negative. And then finally, x squared minus 4 when you plug in a positive 3 is going to be positive. So we just want to know, when is it positive? It's positive in these regions right here. I'll go ahead and highlight them. This region is positive, and this region is positive. That means x can be anything climbing all the way up from negative infinity all the way up to negative 2. Let me draw that in. And of course, we cannot include negative 2. Then we're going to skip over, and we can't include anything in that middle region because in that middle region between negative 2 and positive 2, x squared minus 4 is actually negative, so that doesn't work out. We want all of our values to be positive. So we are going to start back up at 2. We cannot include it, and we're going to climb up to infinity. So that's our domain for this third function. So again, those are the three conditions that restrict domain. Now, if you go back up to our previous example here, g of x is equal to 3.18 x to the 15th minus x squared plus 1.2. There's no division there. You're not going to be dividing by a variable, so you don't have to worry about that. You don't have any radicals, so you don't have to worry about that. And you don't have logarithms, so you don't have to worry about that. So in this case, nothing restricts the domain. And I get that the domain is all real numbers. There's two ways to write that. There's actually a lot of ways to write that. You can either write it as an interval. This is called interval notation, recall. Negative infinity to positive infinity. Or you could write it as a set. The set of real numbers. Now finally, the only thing else I need you to know here is that the coefficient on your highest degree term is called the lead coefficient. So I need that in our vocabulary because we are going to use that language as we go through polynomial functions. And I went ahead and wrote that in down there. Also, by the way, that lead, the term that has the lead coefficient is called the lead term, just so you know, just in case that sneaks into a problem on your homework from your instructor.